Hi students. In the second video for chapter 6, we are now going to talk about two important properties of our covalent compounds, and that is bond length and bond enthalpy. So let us go compare our ionic compound, which was chapter 5, with the covalent compounds that we introduced in the last video. Notice that their melting points are drastically different. The melting point is a judge of how much energy it will take to break the interaction between molecules. For the sodium chloride, that temperature is incredibly high. This means that there is a great interaction between our molecules, while for our carbon tetrachloride, there is a little bit of an interaction. The other point you can see here is that with the boiling point, you are going to see a very high boiling point and a fairly low boiling point for the covalent compounds. Another thing you'll see is that ionic compounds are incredibly soluble. This means that they will break up into ions, and we will discuss this exclusively when we get to our aqueous solutions chapter later in this semester. When it comes to our covalent compounds, they do not dissociate or break up into ions, so historically their solubility in water is fairly low. Now let's go look at electrical conductivity. When it comes to our ionic compounds, if they're in their solid form, it is actually a very poor conductor. So sodium chloride, as you would have with table salt, is actually a poor conductor. But once you've put it in solution and those ions break up and they're free floating in solution, it becomes a very good conductor. When it comes to our covalent compounds, they are poor electrical conductors because we're sharing electrons. Electrons are not historically moving in those compounds. It's really important that you start to understand a few of these properties because when you start in chemistry 120 and start discussing the intermolecular forces and some of your solid and liquid properties, it is going to come back to these ideas. So let's talk about covalent bonds to begin. As you saw back in the previous chapters about ionic radius, when we have our covalent compounds, we are going to have overlap. So that means that some of the electron density of the two atoms is going to mathematically merge. That is how you get the picturizations here of where they seem to be a little smushed. But the important part that you want to see here is that if you have a single bond, we can go and estimate the distance of that single bond using the atomic radii with just a little bit of a shortened distance. So in the case of where you have your hydrogen, notice that we have H2 being 74 picometers. If I go and bind one of those hydrogens with an iodine, notice that because iodine, it is a larger halogen atom, as we see in the periodic table, this is going to produce a longer bond length. We will show you what this means about bond strength. So as you can see with our table here, carbon bound to hydrogen is a very small bond length. That is because hydrogen has a small atomic radius. When we go to carbon oxygen, it gets longer. But also then notice if we go to carbon oxygen with a double bond, it gets shorter again. Carbon carbon gets longer, carbon carbon double bond gets shorter, and a carbon carbon triple bond gets even shorter. So there's two different trends that we have to discuss in here. If we have a single bond, we need to go back to the periodic table and look at our atomic radii. If we have a multiple bond, we have to look at its stability based off of its electron density. So in the case of our bond lengths, triple bonds are going to be our shortest. So the two that we want to look in here are our carbon-carbon triple bond and our carbon-nitrogen triple bond. Notice that the carbon-nitrogen triple bond is slightly smaller. The reason this is the case is because nitrogen is slightly smaller, being farther right on the periodic table than carbon. So in this case, what we want to do is say that all triple bonds are shorter than all double and all single bonds, but then, very much like where we had with our lattice energy, we may have to break ties and stability based off of just our normal trend of atomic radii. If we go to our double bonds, then we can look at such species as our carbon-oxygen, our carbon-carbon, and finally our carbon-nitrogen. If you will see, we go from 121 for our carbon-oxygen, then to 133 for our carbon-carbon, and then finally 138 for our carbon nitrogen. So this means that as we are going through that series, a longer bond length means that it's going to be a weaker bond. Finally, as you can see through here, there are going to be single bonds that we must be concerned about. And as our atoms get bigger, our bonds get bigger, and our bonds will get weaker. So let's rank the following bonds in order from shortest to longest. As you can see here, I have the carbon-carbon double bond. I have the NO single bond. I have the HI single bond, the OO double bond, and finally the nitrogen-nitrogen triple bond. So the first thing that we want to do is go and look to see if there are any triple bonds. Notice that I have that here with our nitrogen-nitrogen. This should be the shortest of all of the bonds that I'm going to deal with. So that means that we are going to have answer B, answer D, and answer E not be correct answers. So now what we need to do to separate between C and A is now look at our double bonds. We have our carbon-carbon double bond and our oxygen-oxygen double bond. So which one is going to be shorter? Well, remember that oxygen is farther right on the periodic table than that of carbon. So our individual oxygen atoms are smaller. This means that the bond between the two atoms is going to be shorter. So our oxygen is going to be number 2, and our carbon is going to be number 3. So right now, this should mean that we will get answer C as our correct answer. So now let us go and look at our single bonds. Notice that I have nitrogen and oxygen and my HI. Well, remember that HI is a very long bond, not because of the hydrogen, but because of the iodine. This is going to be longer than that of my nitrogen-oxygen, which are both in my second principal quantum number row. So now what is going to happen is our nitrogen-oxygen will be next, followed by my hydrogen and iodine, and this confirms that answer C is a correct answer. So when using our bond length, we first want to look at what is the bond order. That means, is it single? Is it double? Is it triple? And then if I have multiples of those bonds, I need to look at the atomic radii using the periodic trend that we discussed back in chapter 4. A second way of looking at the stability of a covalent compound is typically what we call bond enthalpy. This is fairly analogous to that of the lattice energy of ionic compounds. Lattice energy for ionic compounds talked about the stability, how much energy we would need to break up a molecule, and this is identical to that for bond enthalpy, but bond enthalpy associates this with covalent compounds. This is the enthalpy change required to break a particular bond in 1 mole of a gaseous molecule. So what do we mean by that? Well, if I take hydrogen, this is taking H2, which is bound together by a single bond, and separating it into 2 gaseous hydrogen atoms. Notice that I get a bond enthalpy of 436.4 kilojoules per mole. So then if I do the same with chlorine, it's taking a chlorine molecule and breaking it into 2 individual chloride atoms. Notice that my delta H is 242.7 kilojoules. This means that that bond was longer and less stable, so it took less energy to break it. The higher the energy for our bond enthalpy means that the bond is stronger and needs more energy put in to break it. So as we go to HCl, you will notice that if I take H and Cl having a bond together and split it, it will then get a delta H of 431.9 kilojoules. So this is a fairly strong bond, but just slightly less stable than that of my hydrogen-hydrogen bond that we started with. As I go to O2, notice that I'm going to separate this now into oxygen and oxygen. But now notice that the energy is 498.7. This doesn't make sense unless you draw the Lewis structure of our oxygen. Our oxygen contains a double bond. So the 498.7 being greater than all of the other energies we've seen here is indicative that we have a multiple bond that is leading to increased stabilization and a stronger interaction between those 2 atoms. As you can see here with nitrogen, we have N2 breaking up into nitrogen and nitrogen. And notice now that we get 941.4 kilojoules. Well, why is that the case? Because we have the nitrogen-nitrogen triple bond. So for our double bonds and our triple bonds, our energies are going to become increasingly higher. You are not expected to memorize any of these values, but if you see a large increase in there, it is indicative of multiple bond characterization. So for our bond enthalpies, single bonds are going to be our weakest bonds. This means that they are going to have the lowest energy. The longer the bond, the smaller our delta H is going to be. Then with our double bonds are getting shorter and stronger. Therefore, our delta H is going to get higher because we need more energy to break them. And that is also the case with the triple bond because we are having more electrons holding those two atoms together. So here are some common bond enthalpy values. You are not expected to know these, but you would be given these on an exam or quiz. But as you can see, it can really help tell you some very important trends when dealing with how atoms are covalently attached. The interesting ones can be seen here with our hydrogen halides. Notice that as we go from HF to HCl to HBr and to HI, that our energy goes down. This is because our halogen bond length is going to get bigger because the halogen atom gets bigger. This is going to help us out greatly. We can also see that for such things in our carbon halogens here as well. And it's really important to notice that as we go down into our halogens bound to themselves, that fluorine actually is one of the least stable. This is because it is so electronegative and would prefer to split apart. That is how it gets an unusually low bond enthalpy. You would use these bond enthalpies to help predict energies of reactions. So how do we do that? Well, just imagine reactions proceeding by breaking all the bonds in the reactants and then piecing them back together to form the products. This is how we can use our bond enthalpy to predict our delta H, or our enthalpies of reaction. So what we're going to look at is our delta H is equal to the total energy input minus the total energy released. So what does that mean? That is the bond enthalpy of the reactants minus the bond enthalpy of the products. Our original reactants are considered endothermic. We have stable compounds and we must add energy in order to turn those into the reactive atoms in our transition state. For our products, those atoms, now at a high energy state, are going to form the products that we want, releasing energy. So our total energy input is going to be endothermic, and that is going to be our reactants, while hopefully our total energy released is going to be exothermic and will be our products. This might differ from what we will get to eventually, where we keep talking about products minus reactants, but in this case, it's better to remember bonds broken minus bonds formed. This is going to be a much better use for you. So let's try a couple of examples. Use the bond enthalpies to calculate the enthalpy of reaction for this process. We are going to take H2 and Cl2 and hopefully form HCl gas. So how can I do that? Well, let us go and do our equation. So that's delta H of our reaction is equal to our energy in, which is our bonds broken, minus our energy out, which in this case is going to be bonds form. So now the question needs to be, what bonds are we breaking? Well, in the case of our reactants, we are going to look and see that we have our H2. So our H2 is going to have one H bond that needs to be broken and one chlorine bond that needs to be broken. So what is our energy of our hydrogen-hydrogen bond? Well, if we go back to our table, that would be 436.4 kilojoules per mole. Then when it comes to my chlorine, I would need to find that value, and that comes out to be 242.7 kilojoules per mole. So now what I need to do is add those two numbers together. So we will take our 436.4 and add that to our 242.7, and you will get a total energy in to break up everything of 679.1 kilojoules of energy needed to break our bonds. So now we have to look at our products. Well, notice that I will form 2 moles of my HCl. So this means that I'm going to have 2 HCl bonds that I need to be concerned about. So this means that I need to look up that value and multiply it by 2. So if I do that, I can get 2 times my HCl value will be 431.9 kilojoules. So if I do that, my energy out is going to be 863.8 kilojoules. So now all I need to do is take my difference, and if I subtract the 863.8 from my 679.1, I will get a delta H of this reaction to be negative 184.7 kilojoules per mole. So this will show you that this overall reaction is going to be exothermic and release energy. So let's try another example. This example comes from my fall 2015 exam and will show you the importance of our bond enthalpy. So first thing I want to do is break up methane, which is a carbon attached to 4 hydrogens. So for this molecule, I need to find the energy of 4 carbon-hydrogen bonds to break. And then for my bromine, I need to have 4 Br bonds to break as well. So that will give my energy in that I need. So that is going to be 4 times my carbon-hydrogen can be found here at 413. So I have 4 times 413 plus 4. Now I need to go and get my bromine, which is found here at 193. And my energy in is going to be 2424 kilojoules needed to go in. So now let us go ahead and look at our products. In this case, you will see that I have 4 carbon bromine bonds that I need to form. And then I also will form 4 HBr bonds. So now I can go and find those on my chart. So for my carbon bromine, you can find this here at 276. And then finally, HBr can be seen here with our 366. So if I go and take my 4 times 276 plus my 4 times 366, I get a value of 2568 kilojoules. That's how much energy I am going to be releasing. So what do? I will take my 2568 and subtract that from my energy going in. If I do that, I get a value of negative 144 kilojoules per mole, and this reaction is going to be exothermic. In this video, you saw some very important trends, not only the comparison of when it comes to our ionic compounds, but now you've seen how bond length attributes to stability, and then finally, how we can use bond length, bond stability, and energy to help us predict our reaction energy using the bond enthalpies. Hopefully this video has helped immensely when coming to talk about the stability of our covalent compounds. Have a great day.